Okay, dear colleagues, I'm happy to start the spring semester of BIM's Integrable System Seminar. And our first speaker is Weyl from Peking University. Please, you are welcome.
Okay, thank you. It's very happy to be here to share our work in this integrable system seminar. But I should say that I almost know nothing about integrable system. So today I want to talk about some asymptotic log-concavity of dominant nor Bruhat intervals via Brunn-Minkovski inequality. And this is drawn with Gaston, Bruhat, and Hongshenhu. Both are postdocs in Peking University. So let me tell about the background of our research. So let G be a complex cosmodic group, or just you can take any reductive or semi-simple group. And B is the Borel subgroup inside G. And let W be the Y group, which is generated by the set of simple reflections as a Coxeter group. And for any subset of inside S, we have a parabolic subgroup denoted by Wj. And we consider the set of minimal representatives for the right coset, W mod Wj. And this, the parabolic subgroup of the Y group, it determines a standard parabolic subgroup Pj of G, which contains the Borel group B. And we have the Bruhat decomposition of this partial flag variety G mod Pj. It decomposes as some disjoint union of this PJWB mod Pj. And this is called the Schubert cell, which topologically is just an affine space of some dimension. The dimension is given by the Coxeter length of W. And let XW be the closure of this Schubert cell. And this is called Schubert variety, which also have the Bruhat decomposition. And the cell inside this Schubert variety is indexed by the elements less than or equal to W in the minimal representatives JW. And this is a Bruhat Chevalier order. For example, you can take this is an example in spinal type A. You can take G to be GLNC, the general linear group, and it contains the Borel group of the upper triangular matrices. And the Y group in this case is just the permutation group. Oh, okay. And the Y group in this case is just the symmetry group of n letters, and it's generated by the adjacent transformations and satisfy some relations. And for n equals 4, the Bruhat Chevalier order is like this, and it's quite complicated. And so I use the red color to indicate the elements between 1, 2, 3, 4 and 3, 4, 1, 2. These two this Bruhat intervals. So what we are interested so you can count how many elements in each layer. So this layer is indexed by the Coxeter length, and you can count how many elements in each layer. For example, if you count all the elements in this Weyl group is corresponding to this sequence 1, 3, 5, 6, 5, 3, 1, which equal the Betti numbers of the finite group, finite flag variety corresponding to GL4C, and or you can just count the elements in each layer inside this Bruhat interval, which reads 1, 3, 5, 4, 1, 1, 3, 5, 4, 1. And this corresponds to the Betti numbers of the Schubert variety corresponding to this Noir interval. So the question we want to understand is this one. So how many I-dimensional cells occur in the decomposition of XW? So we are interested in the behavior of the sequence of the numbers. And we denote by B, BWJI, to be the number of elements in this set of minimal representatives, which is below W, and the length is the length equals I, and this actually equals the dimension of the two eyes cohomology of the Schubert variety. So this is actually the Betti numbers of the Schubert variety, and we are interested in the behavior of these Betti numbers. So here are some known results for this question. In 2009, Björner and Ekedahl, they proved two sets of inequalities. The first one is called top-heavy, which means for any I less than or equal to half of the length of W, this BI is less than or equal to B length of W minus I. And this is called the top-heavy because top is heavy. And the second inequality is set of inequalities is this one. So B0 less than or equal to B1 less than or equal to B half of length of W minus 1 less than or equal to B half of length of W. That is, this sequence is weakly increasing in the lower half. So maybe I turn back here. So maybe we can look at this sequence, this red sequence. So 1, 3, 5, 4, 1. So 3 is less than 4. This is the top-heavy inequality. And 1, 3, 5. The first half is weakly increasing. So this is their results. But the proof is actually, the paper is published on in the ALOS, because the proof is they use some fancy tools like Hodge theory or some perverse shapes. It's very complicated. And actually, you can generalize these results to any Coxeter groups. Although for a general Coxeter group, you don't have a black variety or Schubert variety, but you can also define this these numbers, and you can ask the same question, and you can use the LS and Williamson's results on the Hodge theory of so-called bimodule to prove same inequalities for any Coxeter group. And there are some parallel or similar results for the world of hyperplane arrangement and for matrix. This is our work of Ha and his collaborators. And these two work are important work of Jun Ha, and won the field medal in 2022. So these are the known results. And what we want to understand is some other numerical inequalities called log-concavity and unimodality. So a sequence of real numbers is called sorry, I misspelled it. Log-concave, meaning that for any I greater than 0, less than or equal to, and we have this quadratic inequality. AI squared is greater than or equal to AI minus 1 times AI plus 1. And this sequence is called a unimodal. If you have a unique mode, unique peak inside this sequence, for example, there exists a K such that A0 less than or equal to A1 less than or equal to AK. And then, so it's first increasing and then weakly decreasing. So the conjecture, so Brunt conjecture that if you begin with the Y group and adding two elements of this group, then the sequence of the length-enumerating sequence of this Bruhat interval inside this Y group is log-concave, hence unimodal. But this conjecture is very difficult. And actually, this conjecture doesn't hold for general parabolic lower Bruhat intervals, i.e., you can't take some parabolic subgroup and consider this question in for the minimal set of minimal representatives. For example, you can consider this Grassmannian 412, which is a partial flag variety, and inside this Grassmannian, you have a Schubert variety indexed by this partition 8844. And if you compute the length enumerating sequence, it reads like this. It increases in the weekly increase in the first half, but doesn't be unimodal. So even for Y group, you cannot take lower parabolic intervals. So, but our setting is is slightly different. So our setting is that let phi be a root system of rank R of some simple Lie algebra in the Euclidean space E with this inner product, and let delta, this alpha I, be the set of simple roots, and let W F be the finite Y group generated by some simple reflections. And we consider W to be the semi-direct product of the coroot lattice with the finite Y group, which is the affine Y group. It's defined by to be the group of affine transformations generated by affine reflections along some hyperplanes. So I will show if you are not familiar with affine Y group, I will show you some picture. But by definition, the affine Y group is a group of affine transformations on E. So it acts on E and preserves this hyperplanes. So then it acts on E minus this hyperplanes, and then it acts on these connected components, which are called alcoves, the set of alcoves. And if you fix an alcove called the fundamental alcove, this gives you a one-to-one correspondence between the affine Y group, between the elements of affine Y group and the alcoves. So that is, this action is simply transitively. So this is our favorite example, affine type A2. So we have this 6 roots, and this alpha and beta is the simple roots. And you have this the points. These points are the how to say, the root lattice, and this blue region is called the dominant Weyl chamber, and the affine Weyl group is generated by the affine reflections along these hyperplanes, and these hyperplanes cut this plane into some triangles, small triangles. These triangles are the alcoves, and if you choose if you fix a fundamental alcove, then you can ask where an element W X transform this fundamental alcove into another alcove, and this gives you the one-to-one correspondence between the elements of affine Weyl groups and the alcoves. And actually, this affine Weyl group is a Coxeter group, which is generated by the reflections along the walls of the fundamental alcove. And how to compute the length of an element? It's just the hyperplanes separating the fundamental alcove and the alcove representing W. But the Bruhat-Chevrolet order is more tricky, and we can only understand it locally. So understand the Bruhat order in an affine Weyl group is a difficult task. But however, we can consider this quotient. So if you quotient take the quotient W module WF, and this FW is the minimal representatives, is a set of minimal representatives of this quotient. This many questions are simpler, because in this case, an element W in the affine Weyl group is in the belongs to this minimal set of minimal representative is equivalent to this fact that is the alcoves corresponding to W is contained in the dominant Weyl chamber. And you can compute the length of some translation. This translation is in this affine Weyl group by some by the inner product of the 2 rho with lambda. Here, this rho is half sum of the y vector, the half sum of the positive roots. And if you fix two points in the coroot lattice intersect with the dominant Weyl chamber, the closure of the dominant Weyl chamber, they are T mu less than or equal to T lambda in the Bruhat-Chevrolet order. This is equivalent to that lambda minus mu is a non-negative linear combination of the simple coroots, and it's also equivalent to that mu is contained in the convex core of the final Weyl group orbit of this lambda, and this convex core of this final Weyl group orbit of lambda is called a weight polytope. So again, I will show you picture. So so this blue region is the alcoves in the dominant Weyl chamber, which corresponding to the elements in the FW, the set of minimal representatives of W modulo WF, and you can compute the length of each element, each alcove, by counting how many hyperplane separating this fundamental alcove with your given alcove. So for example, here the fundamental alcove has length 0. This alcove, the alcove, then here is an alcove of length 1 and the 2 alcoves of length 2, and so on and so on. And then you can write down the length enumerating sequence that we are interested in. It reads 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 4, 4, 2, 1. So you can observe that this sequence is unimodal, right? This sequence is weakly increasing until some points and then weakly decreasing. But it's not log-concave, right? 1 square doesn't, is less than or equal to 1 times 2, for example. So before I present our results, I want to talk about some motivation constructions which motivates our construction. So the first one is called the Ehrhart polynomial. So that is, let P be a lattice polytope in Rn. So a polytope in Rn is just the convex whole of some points in Rn. And the lattice polytope means every vertices of this polytope is a lattice point in a given lattice. So given a lattice polytope in some Euclidean space, you can compute this function. That is, you count the lattice points of this lattice in the t-fold dilation of this polytope Tp. You count this number, and of course, this is a function in T. And Ehrhart proved that in 1962 that this is actually a polynomial with rational coefficients, and the leading coefficient is the volume of this polytope under some normalization of the big measure. So from this, you can deduce that the volume of this polytope is just the limit of this function divided by t to the n, right? Because this is a polynomial. So if you know some theory of toric variety, you know that a lattice polytope, the normal fan of this P gives you a toric variety, and the Ehrhart polynomial of this polytope is equal to the Hilbert polynomial of the ample line bundle defined on X by P. And this equality, this limit result is just implied by the asymptotic Riemann-Roch theorem. So this is the first motivating construction. The second is called the Duisman-Heckman measure. So let G be a compact Lie group, for example, SUN, and let T be the maximal torus inside G, and let lambda be a dominant weight of T, and from the highest weight theory, this lambda corresponds to a highest weight irreducible representation of G. Let me denote it by V lambda. And this V lambda is an irreducible representation of G, but it decomposes as a representation of T. Like this. This is called the weight space decomposition. So every V lambda mu is eigenspace of this maximum torus, and you can and we are interested in the dimension of every weight space, and this dimension is called the weight multiplicity. And for the special case of G equals the special unitary group, this weight multiplicity is known as the Coxeter. And people are interested in the behavior of this weight multiplicity, but if you are given for a given lambda and mu, you can compute this number by the famous Weyl character formula. But we want to understand the global behavior of this weight multiplicity. And Heckman, in 1982, in a paper in Invention, so let me explain this this formula, which looks like complicated. So we are interested in this weight multiplicity, and because lambda is the dominant weight leaving the weight lattice, so we can consider the k lambda. So k lambda is also a dominant weight, and you can consider this this weight multiplicity, and you compute this weight multiplicity after dilation, after k dilation of this dominant weight, and put a direct measure on this mu over k, this point, and take summation over all weights mu, and so this is a discrete measure given by the weight multiplicity, and you divide it by the total mass. So this normalization gives you that this total measure of this discrete measure equals 1. And for any k, you can compute this. You get a discrete measure, and the result is when k approaching infinity, this sequence of discrete measure has a weak limit of a continuous measure given by this push forward of the Lebesgue measure on the co-joint orbit by the moment map. So so every lambda gives you a co-joint orbit inside the Lie algebra of G, maybe the dual, and the group G acts on this co-joint orbit and preserves the symplectic structure. So this is a Hamiltonian action. So you have the moment map, then you push forward the Lebesgue measure of this co-joint orbit by this moment map, and this push forward measure is just the weak limit of this discrete measure, and actually this is a continuous measure. And later, this density function of this continuous measure proved to be log-concave by Graham. So this two motivating construction of our paper. So for example, you can consider the type A2 case. So so take lambda equals rho, the half sum of the positive roots. Then you have this weight multiplicities, and then you dilate this lambda, and then scaling back, you have a more denser lattice points, and it gives you the so each lattice point in this denser lattice is decorated with multiple weight multiplicity, and you have some distribution. And you do dilation and scale back. This sequence of discrete measure, you have denser and denser lattice points, and then this sequence of distribution, this sequence of measures tends to a continuous measure supported on this weight polytope. And the limit the density function of that limiting measure is log-concave. Finally, another important motivating construction is a so-called Newton-Konkov body in Konkov's paper, Brunn-Minkovski inequalities for weight multiplicities. But this construction is much more complicated, and I will skip. So let me explain our results. So let the sequence, the length-enumerating sequence, be this Bi T num F, which means we consider the affine Weyl group, module Weyl group, and the element W corresponding to a transformation indexed by a coroot lattice in the coroot lattice point in the dominant Weyl chamber. And we consider this polytope defined to be the convex hole of the finite Weyl group orbit intersect with the closure of the dominant Weyl chamber. And we have the linear function from this polytope to the real number called height. So it computes the height or length of the points. So our theorem is that also you can, because this lambda is living inside this lattice, so you can talk about dilations and dilations. And you dilate this sequence and scale back to by putting a Dirac measure on the point I over k, and the summation over I, and then divided by k to the r. This sequence of discrete measure weakly converges to the push forward of the big measure of this polytope under this height map up to a normalization constant of the big measure. And the second result is that is a uniform convergence. So you can define a step function using this sequence. So I will. So for any x in this interval 0 to length of t lambda, there exists a unique I belong to 0, 1, k times length of t lambda, such that x is inside this interval, this smaller interval. Then as k of x is defined to be the value of this bi divided by k to the r minus 1. This sequence of step functions uniformly converges to the density function of the about limiting measure. So let me again explain our results by some pictures. So what we are interested in is the length-enumerating sequence of these Bruhat intervals. So you put the number bi in every point I. So you have some picture like this, and then you dilate this lambda. For example, here is the 6 lambda. So this gives you more numbers, but you scale back to such that these numbers, you put these numbers on the original interval 0 to length of t lambda, and you dilate and dilate this. The shape of these pictures then will converge to this continuous function, which is given by the volume of the hyperplane sections of some polytope. So then from this picture, so you see that the original problem we want to prove is that this final sequence is unimodal or log-concave, but it's very hard to prove this kind of results. But what we can prove is that this discrete question, it converges to some continuous function, and this continuous function is log-concave. So this is our results of asymptotic log-concavity. So a first corollary of our uniform convergence result is that you consider this sequence bki, tk lambda, f, and divided by k to the r minus 1. That is, you consider the sequence of numbers of each layer in your dilation process. Then this sequence converges to the volume of some hyperplane sections of our polytope up to a normalization constant. And by the classical Brunn-Minkovski inequality, which says that if you have a convex body in a real vector space L1, and let P be a linear transformation from L1 to L2, then the volume of the slice of this convex body, when you take square root of this difference of dimensions, this is a continuous function, and is a concave function on the image of this linear transformation of M. Sorry. Oh, so I forget write the corollary of this Brunn-Minkovski inequality, that this limit, the density function of our limit measure is log-concave by this Brunn-Minkovski inequality. So so finally, I want to talk about some how we prove this kind of results. So this is our dominant. This is by our dominant lattice formula. So So we are interested in this length-enumerating sequence, and it's very typical in combinatorics that when you are given a sequence, you put them together into a generative function. So we call this the Poincaré polynomial of this sequence. And also we have corresponding to this T lambda. So we also have the Poincaré polynomial of the finite Weyl group. So just so this is the generative function of the cost of length of the finite Weyl group. And for any standard parabolic subgroup and the minimal representatives, we also have the Poincaré polynomial of this IWF. So the dominant lattice formula is a formula relating the Poincaré polynomial of this. So this translation of the affine Weyl group by some lattice in our polytope intersecting with the coroot lattice and the Poincaré polynomial of the this set of minimal representatives. So again, I will explain this by a picture. Oh, sorry. So here is a picture. So what we are interested in is in this dark blue region, the alcoves in this dark blue region, and we want to know how many elements of each length, and then you can see that every so this black dots are the lattice points, and you can see that there are 6 alcoves around each lattice points. So 6 is the catalog of the finite Weyl group, but we don't want to count all the alcoves. We only want to count the alcoves inside this dominant Weyl chamber. So when your lambda is here or mu here, you need count 6 elements inside this dark blue region. But when your lattice point is in this wall of the Weyl chamber, for example, this mu, you only want to count 3 alcoves in this dark blue region. So this is why you want to consider the Poincaré polynomial of the set of minimal representatives of the finite Weyl group module some parabolic subgroup. So it depends on whether you are not whether or not you are in this wall. So let me give the summary of the ideas of our research. So we are beginning with the counting problem, counting the cells or the Betti numbers of some Schubert variety. Schubert variety. But this is a very difficult problem. So we consider some special case of this problem. That is the cells inside this affine Weyl group module the finite Weyl group. And in this context, this question is transformed to the geometry of the alcoves. Then by our dominant lattice formula, we can transform this question in this alcove geometry to the geometry of the coroot lattice, but use the same spirit as Ehrhart's theory or the asymptotic Riemann-Roch theorem. we can relate the lattice points and the volume of some polytope. So this this question of geometry of lattice transformed into the question of metric geometry. So we need to compute some volumes of some polytopes, and then by the Brunn-Minkovski inequality, Brunn-Minkovski theory in convex geometry, the Brunn-Minkovski inequality gives us the log-concavity. So this step gives us the convergence, and this final step gives us the log-concavity. So this combined, we get some asymptotic log-concavity results. So finally, simple illustration of our idea. So we begin with the counting problem of something like this. So so this problem of Alcove geometry, but because our element is indexed by some lattice points, you can do dilations and scale back. So you have denser and denser lattice. Then finally, so when you take more larger and larger dilation and scale back, the difference of this Alcove geometry and this convex geometry or metric geometry tends to 0, and then you can prove some results using tools in convex geometry, and this is our idea. So finally, I want to state a conjecture that is our original sequence Bi T lambda F is unimodal for any dominant with coroot lattice lambda. So we have tested this conjecture for hundreds of intervals in rank 3, rank 2, and rank 5 root system with a software Sage Math. And this conjecture holds in rank 2 by some simple plane geometry. But this conjecture, we think this conjecture is very difficult because we have this remark that this sequence is not necessarily log-concave, so it's just a unimodal. So if you begin with a positive log-concave sequence, so log-concavity plus positivity implies unimodality. But our sequence is usually not log-concave; it's only unimodal. And I don't know any non-trivial results. So I don't know someone who can prove unimodality without proof log-concavity. I don't know any kind of technique to do this task. So maybe this conjecture is beyond our technique. So so that I will stop here. Thank you.
Okay, thank you for your talk. Any questions?
I really don't understand exactly what is the asymptotic log-concavity.
Oh.
Because a very standard notion was asymptotic log-concavity, where is for any integer r, where is what is called r log-concavity, and if r is statement valid for any r, it's called infinite log-concavity.
Yeah, but no, our result is not nothing like this. So we begin with a finite sequence, but and then we can use this sequence to construct some discrete measure or some step function. Just you how to picture this sequence. You put the numbers inside these intervals, and then because we can do dilations, you have more and more numbers. Then this sequence of measures or functions, they are convergent to some continuous functions, and the limits function is log-concave. This is our meaning of
different.
Yeah, it's different.
And another natural question is, what happens if, for example, for type A, you can study what you study really, this is called the stretch Koska numbers, but you can study really not Koska numbers, but Koska polynomials, and consider similar expressions for Koska polynomials. And what I know well, it's for type A. For arbitrary type, I don't know. But this kind of expression also have a limit, and this limit related with the characters of affine algebras and so on. And it is also interesting questions about connection of this object, not with exactly volume, but with generating functions for number of integer points in this convex hull.
So sorry, I don't know. I don't know the.
What happens if you consider your theory not for
numbers, but for
multiplicities, but QA multiplicities?
Yeah, the Q analogs. Yeah. I don't know. I don't know any results in this kind of generation.
Maybe the last question, because there are too many questions. This is very simple things, questions. You study, for example, symmetry group.
Yes.
And you study what is called a relation, classical representation of symmetry group is a group generated by simple transpositions.
Sorry?
And there is Bruhat theory, Schubert, so on. But what happens in your case if you consider another set of generators of symmetry group? For example, the most interesting, okay, for example, you can take all generators, all elements of generators of your group, all transpositions. Is it when you can compute Hilbert Hilbert series of polynomials of this theory? That means you consider reduced primitive decomposition of elements of symmetry group in terms of all transpositions.
Yeah, I think I understand the. I understand the question, but I don't know the question.
Because this is very interesting questions about unimodality with polynomials and log-concavity, and interesting what is called star generators of symmetry group and so on.
Sorry, I don't know the answer to this question.
Just a short question. You say that in general log-concavity is false, and therefore there is no hope to have this unimodality. But maybe for some cases, like for the symmetric group itself, for the A series, is it true or is it also false?
So we have some example in type A that is not our sequence is not log-concave even in type A. Yeah. Yeah, this picture is in type A.
Okay, any questions from Zoom? Okay, if not, let's thank the speaker again.